Okay, just got back. Figure I'd get on and do at least an hour here. Alrighty. So we finished 226. Okay, we're starting on a new section, integer arithmetic. Many beginning programmers are surprised to find that adding two positive numbers can yield a negative result, and that comparisons x minus y can yield different results than comparisons x minus y is less than 0. These properties are artifacts of finite nature of computer arithmetic. Understanding the nuances of computer arithmetic can help programmers write more reliable code. Unsigned addition. Consider two non-negative integers, x and y, such as x is greater than or equal to 0, and y is less than 2 to the w. Each of these values can be represented by a w-bit unsigned number. If we compute their sum, however, we have a possible range of I guess I'm kind of confused why we selected these values. So consider two non-negative integers x and y, such that x is just greater than or equal to 0, and y, so x could be way farther. X could be a quadrillion. There's nothing bounding x in this statement. And then y is bounded by 0 because it says that it's not negative. So it's between 0 and 2 to the w. So each of these values can be represented by a w-bit unsigned number, because y is less than that. Y is not equal to that. If we compute their sum, however, we have a possible range 0 less than or equal to x, plus y, which is less than or equal to 2 to the w plus 1. Okay, that's a plus 1, not a minus 1, minus 2. Representing this sum, you could require w plus 1 bits. For example, because it could be 2x to that value. For example, figure 2.21 shows a plot of the function x plus y when x and y have a 4-bit representation. The arguments shown on horizontal axis range from 0 to 15, but the sum ranges from 0 to 30. The shape of the fraction is a sloping plane. The function is linear in both dimensions. If we were to maintain the sum as w plus 1 bit number and add it to another value, we may require w plus 2 bits and so on. This continued word size inflation. Let's see. So if we got 4 bits wide, we could have value of all 4 set, which would be 15. And then if we take this one to 15, then our value is 32. 15, 15. Shouldn't that be 30? Oh, but we go up to 32 because each one of these units here is a unit of 2. That's a unit of 1, this is a unit of 2. 2, 4, 8, that's why it goes up there. One, 2, 3, 4, 5, 6, 7. Okay, 15. So this continued word inflation means we cannot place any bounds on the word size required to fully represent the results of arithmetic operations. Some programming languages, such as Lisp, actually support arbitrary size arithmetic to allow integers of any size within the memory limits of the computer, of course. More commonly, programming languages support fixed size arithmetic, and hence operations such as addition and multiplication differ from their counterpart operations over integers. Let us define operation plus between u and w for arguments x and y, where 0 less than or equal to x and y is less than 2 to the w, as the result of truncating. Maybe that means that both of them, x and y, are both in that condition, not. See, when I was parsing this statement, I thought this was a separate statement and this is a separate statement. But it could be this is a whole one statement where these two values are greater than or equal to 0 and less than 2w. That would make more sense. Okay. As a result of truncating the integer sum x plus y 2w bits long and then viewing the result as an unsigned number, this can be characterized as a form of modular arithmetic, computing the sum modulo 2w by simply discarding any bits with weight greater than 2 to the w minus 1. In the bit level representation of x plus y, for example, consider a 4-bit number representation with x is equal to 9, y is equal to 12, having bit representations 1001 and 1100 respectively. Their sum is 21, having 5-bit representation. But if we discard the high order bit, we get 0101, that is a decimal 5. This matches the value 21 mod 16, which is equal to 5. Makes sense. You just wrap around. Okay, security vulnerability and get peer name. It's interesting. In 2002, programs involved in the FreeBSD open source operating system project realized that their implementation of the get peer name library function had a security vulnerability. A simplified version of their code went something like this: illustration of code vulnerability similar to that found in FreeBSD's implementation of get peer name, declaration of library function memcopy. So we got memcopy into destination from the source size tm, where size t is a unsigned value. Kernel memory region holding user accessible data. So there's a kernel buffer 1024. Okay. Copy at most max length bytes from kernel region to user buffer. Copy from kernel to the user destination and max length. Byte count length is minimum of buffer size and max length. So the length is k size is less than max length, then it's going to be k size. If it's greater than or equal to max length, then we do max length. And then we memcopy user destination k buffer length. I mean, that seems pretty reasonable to me. I guess memcopy could return, it returns a void star, never mind. Oh, this is going to have to do it because K size is just a constant. Or it's just a constant. Max length is an integer. Huh. I'm actually not really sure what the bug is on this one. Oh, memcopy is a size T. That's the bug. So you got memcopy, which takes in an argument which is signed, and you're passing in an argument which is a integer value. And if that happened to be negative, which it would be if you passed in max length as a negative value, then you would copy a huge amount of data. Yeah, that's the bug there. So max length can be passed in as negative, which would evaluate this entire expression to be negative. The negative value would go into memcopy. Memcopy then interprets it as a signed value, and it's like a huge signed value, and it just starts copying all the kernel memory into user memory. In this code, we show the prototype for the library function memcopy at line 7, which is designated to copy a specified number of bytes n from one region of memory to another. The function copy from kernel, starting at line 14, is designed to copy some of the data maintained by the operating system kernel to a designated region of memory accessible by the user. Most of the data structure maintained by the kernel should not be readable by a user, since they may contain sensitive information about other users and about other jobs running on the system. But the region shown as kbuff was intended to be one that the user could read. The parameter max length is intended to be the length of the buffer allocated by the user and indicated by argument user destination. The computation at line 16 then makes sure that no more bytes are copied than are available in either the source or destination buffer. Suppose, however, that some malicious programmer writes code that calls copy from kernel with a negative value of max length. Then a minimum computation on line 16 would compute this value for length, which would then be passed to the parameter n to memcopy. Note, however, the parameter n is declared as having a type size t. This data type is declared via typedef in the library's file standard.io.h. Typically, it is defined to be unsigned for 32-bit programs and unsigned long for 64-bit programs. Since argument n is unsigned, memcopy will treat it as a very large positive number and attempt to copy that many bytes from the kernel region to the user's buffer. Copying that many bytes, at least 2 to 31, will not actually work because the program will encounter invalid addresses in the process, but the program could read regions of the kernel memory for which it is not authorized. That's an interesting old bug. We can see that this problem arises due to the mismatch between data types. In one place, the length parameter is signed. In another place, it is unsigned. Such mismatches can be a source of bugs, and as this example shows, can even lead to security vulnerabilities. Fortunately, there were no reported cases where a programmer had exploited the vulnerability in FreeBSD. They issued a security advisory, FreeBSD SA 238 signed error advising system administrators on how to apply a patch that would remove the vulnerability. The bug can be fixed by declaring parameter max length to copy from kernel to be of type size t. To be consistent with parameter n mcopy, should also declare local variable length and the return value to be of type size t. But you could still pass in a negative value. But I guess they would get caught by the length, because the negative value would then be interpreted as a very high value. we can characterize operation plus UW. Didn't we already discuss that before? Plus UW, yeah. As follows: principle, unsigned addition. For x and y, such as 0 is less than or equal to x, and y is 0 is less than or equal to x and y is less than 2 to the power w, and x plus uw. So that's unsigned addition between x and y, treating them both as unsigned, of length w. Then x plus y when x plus y is less than 2 to the w, that's normal. And then the overflow condition is where the sum is above 2 to the w, or equal to or above 2 to the w, and less than 2 to the w plus 1. You cannot exceed that. Then x plus y minus 2 to the w. So you just subtract the 2 to the w. This is a modular summation. Basically, throw away the bits that overflow. The two cases of equation 211 are illustrated in figure 222, showing the sum x plus y on the left mapping to the unsigned w bit sum on the right. The normal case preserves the value of x and y, while the overflow case has the effect of decrementing the sum by 2 to the w. Derivation. Okay. Derivation. Alright, I'm going to look ahead a little bit here, just see what we got ahead of us. So we got some problems, then we got 2's complement addition, how that behaves, its properties, and 2's complement negation, unsigned multiplication, 2's complement multiplication. Lots of practice problems. Multiplying by constants. Dividing by powers of 2, which is a right shift. Final thoughts on integer arithmetic. And then we get into floating point. So it takes us to 144. It's about 22 pages, lots of problems, different operators. And then we get into floating point. We got about 40 pages on floating point. Whew, this is a lot of stuff. In general, we see that if x plus y is less than 2 to the w, the leading bit in the w plus 1 bit representation of the sum is equal. Sum will equal 0. What about underflow? They don't discuss underflow, which is does the same thing. In general, we see that if x plus y is less than 2 to the w, the leading bit in the w plus 1 bit representation of the sum will equal 0, and hence discarding it will not change the numeric value. On the other hand, if 2 to the w is less than or equal to x plus y, which is like less than or equal to 2 to the w plus 1, the leading bit in the w plus 1 bit representation of the sum will equal 1, and hence discarding it is equivalent to subtracting 2 to the w from the sum. And arithmetic operation is said to overflow when the full integer result cannot fit within the word size limits of the data type, as equation 211 indicates. Overflow occurs when two operands sum to the w or more. Figure 223 shows a plot of the unsigned addition function for word size w is equal to 4. The sum is computed modulo 2 to the 4 is equal to 16. When x plus y is less than 16, there is no overflow, and x unsigned addition of 4 bits of x plus y is simply x plus y. This shown as a region forming a slope plane labeled normal, and it's modulo. So these are all the values that can fit within that word size. And as soon as you go over, it overflows. When x plus y is greater than or equal to 16, the additional overflows having the effect of decrementing the sum by 16. This shown as a region forming a slope plane labeled overflow. By executing C programs, overflows are not signaled as errors. At times, however, we might wish to determine whether or not overflow has occurred. Principle: detecting overflow of unsigned addition. For x and y in the range 0 is less than or equal to x and y less than or equal to u max w, let s equal to the sum and the computation of s overflowed if and only if s is less than x, or equivalently s is less than y. Okay. As illustrated in our early example, we saw that 9 plus 12 is equal to 5. You could see that overflow had occurred since 5 is less than 9. Okay, now we got a derivation of that. Detecting overflow of unsigned addition, observe that x plus y is greater than or equal to x, and hence if s did not overflow, we will surely have s is greater than or equal to x. On the other hand, if s did overflow, we have s is equal to x plus y minus 2w. Given that y is less than 2w, we have y minus 2w is less than 0. And hence s is x plus y minus 2w is less than x. Okay, I trust you. Write a function with the following prototype. This would be 2.27. Write a function with the following prototype, which is int you add okay, and you give it what? Unsigned x and unsigned y. Oops. And what we're going to do here, this function should return 1 if arguments x and y can be added together without causing overflow. Well, we just add them together, x plus y, and say if that is less than x, then that's your result. Or we could do the inverse, which is greater than or equal to x. Then they didn't overflow. Okay, let's go ahead and check that. I'll just go ahead and wrap this in C. And if we check, where are we at here? Oh, they did a much larger, oh no, that's a different function, 2.7. Yeah, they use an extra variable, that's unnecessary. but this function is a direct implementation of the rules given to determine whether or not an unsigned addition overflows. Pretty straightforward. Modular addition forms a mathematical structure known as an abelian group. Ooh, interesting. Modular addition forms a mathematical structure known as an abelian group, named after Norwegian mathematician Niels Henrik Abel. That is, it is commutative. That's where the abelian part comes in, and associative. It has an identity element to 0, and every element has an additive inverse. Let us consider the set of w-bit unsigned numbers with addition operation plus uw. For every value x, there must be some value negative uwx such that negative x plus x is equal to 0. This additive inverse operation can be characterized as follows. Principle. Unsigned negation for any number x such that 0 is less than or equal to x, which is less than or equal to 2 to the w, its w-bit unsigned negation x is given by the following. So negative x if x is 0, and then 2 to the w minus x is greater than 0. This is for unsigned. To find its negation. To say it was 3, then it'd be a very big number. So you want to overflow back to 3 is the goal. So say we have a 4-bit value here. So say we have 3, 0, 0, 1, 1. We want to find its negative. So then you'd say to the w, which would be like that. To the 4. This is to the 0, to the 1, to the 2, to the 3, to the 4. So it's to the 4 minus x. So that'd be minus these 3 bits. So you'd subtract off there, giving you all 1s. That'd be the first subtraction. That'd be the second subtraction. And that would be the third subtraction. Well, let's try doing this again. So you got 3, was it 16? And then we're going to have a 16 minus 3, which would be what value? 13. So 13 is going to be 1, 0, 1, 0 for 10. It's 8, 9, 10, 11. So 8, 9, 10, 11, 12, 13. Yeah, that's what I got before when I did the subtraction. 8, 9, 10, 11, 12, 13. So these are the additive inverse. So if we add these together, they should equal 0. So let's add them together. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. So you got a 0 there. Carry the 1. 1 plus 1 is 0. And then 0. And then 1. Yep. So you go to 16, subtract that, you go to 0. Yep. Makes sense. We can represent a bit pattern of length W, which is 4. Okay, let's do 2.28. Okay, we can represent a bit pattern of length W4 with a single hex digit. For an unsigned interpretation of these digits, use equation 212 to fill out the following table and give the values in the bit representations in hex of the unsigned additive inverse of the digit shown. Okay, let's go and do our table. Something like this. And we're going to have what? I think I want to do like that. Well, okay. How many columns? Let me just regenerate another table here. So we got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So 4 by 7. 4, 1, 2, 3, oh, come on, piece of shit. There we go. Can I clear? Nope. I don't want to do that. Okay. Say X. X. Minus X. Say minus X here. You got hex decimal. Hex decimal. Oh, these are decimal hex, sorry. One, 4, 7, A, E. Generate, copy to clipboard. Let's break that down. Move this there. Alright, decimal of hex is 1, 4, 7, A is 10, E is 14. Because, oops, I think I prefer it to be like that. A, B, C, D, E. Yep, 14. Okay, the negative X, which is the inverse, you take to the W, which would be 16 in our case, and you subtract away X. So it'd be 16 minus 1, which would be 15, which would be F. So F, actually let's go back over here, can fix these as well. So 15, negative 15. I guess you'd say negative. I guess it's positive. 15 plus 1 would be 16, would be 0. That seems wrong. 1, 2, 3, 4. So right now we have 1, which is 0, 0, 0, 1. And we have 1, 0, 0, 0, 0. So it'd be 1 and 16 here. If you subtract 1 from 16, I would say you get 15. Go on a limb here. And 15 would be represented as 8 plus 4, 12, 13, 14, 15. It'd be all ones, it'd be F. But if you subtract all ones from, or add them, go back over to here. To the W minus X, 15. It should be F, but the property of the principle is for any number X, its W bit unsigned negation is given by the following. Oh, it's supposed to equal 0. Its inverse brings it to 0. Okay. For some reason, I thought it brought it all the way back to itself. Okay, so decimal 5. So I can just these in my head. The negation from 16 would be 11. 11 would be B. Sorry, 11 B. 7 from 16 would be 9. And 9 is just 9 here. We have 10. 10 from 16 is 6, which is just 6. And E is 14. 14 from 16 is 2. That'll be 2 here. And we'll just pick one out here. To say we have 10, which would be 1010. And then the other one you have is, I need one space here. 10 is 6, so it should be 0, 1, 1, 0. So 0, doesn't matter which order, but 0 and 0 is 0, 1 and 1, 0 carry the 1, 1 and 1, sorry, would be 0 carry the 1, 1 and 1, 0 carry the 1. Yep. Okay, so I think that's the right answers. Let's go to the table. Let's see, 15F, 11B, oh no, there's a 12C for 4. Oh, I made a typo. I made a typo. My hex, I meant to say decimal 4 here, obviously. So then this would be 12 in C. Okay. So 4412C, 7799, A1066, and then we get E1422. Yep. Okay, that's all correct. Just to read the text of the answer, it says this problem is a simple demonstration of arithmetic modulo 16. The easiest way to solve it is to convert the hex pattern to an unsigned decimal value. For non-zero values of x, we must have, then we convert the complemented value back to hex. Okay, not the way I did it, but got the same answer. Alright, so it takes care of that. Now we're in 2's complement addition. So that would be over here. With 2's complement addition, we must decide what to do when the result is either too large, positive, or too small, negative, to represent given integer values x and y in the range so and so. Their sum is in the range so and so, yeah. Potentially requiring w plus 1 bits to represent exactly as before. We avoid ever expanding data sizes by truncating the representation to w bits. The result is not as familiar mathematically as modular addition. However, let us define x of 2's complement addition of w bits plus y to be the result of truncating the integer sum, x plus y to be w bits long, and then viewing the result as a 2's complement number. Okay. I always thought you just wrap around, but maybe I'm wrong. Oh, there's a nice little pretty diagram here. So positive overflow goes negative, yep. Negative overflow goes positive, yep. And then normal is normal. That's exactly what I would have expected. I don't think I really need to go deep into this. Yeah, I think I need to change my study behavior a little bit different here, because I'm not making a lot of progress on this stuff. It's taking forever, and I read through the math and I'm not really grokking all the math. I think they're throwing a bunch of math in here that is like great if you're going to be like an academic about things, but I'm not a mathematician, and while I like math, some of these things are just obvious. And I always think it makes sense to like describe them in such laborious mathematical methods, but I don't know. Maybe I stick with it until at least floating point. But it just seems like a lot. Alright, I'm gonna take a quick break here. Actually, you know what? It's 9 o'clock. I really do need to get into bed. So I think I'll wrap here for the night. That was nice. I got another like 45 minutes in. But I do need to start winding down at 9. Probably should be winding down earlier than that. Okay, so tomorrow I think I have most of the day free. No gym. Just need to do a check-in in the morning, and then I'll hop on and I'll continue reading from here. So I'll do my little marker in the book to let me know where I left off. And yeah, pick up on this tomorrow. Let me do a commit before I log off. Just say get status, get at all, get status, vim, DC. So I did watch the lecture, and that should vim up the chapter 02 data tmin and delete that space there. Okay, let's go down here. Word size C version, I need to fix that. I'll just search for it. There's 2 there. And then there's a thing at the end of this file. Chapter 02 test tmin literals. And then vim chapter 02 problems. And I just want to search for white space followed by new line. Can I search for that again? Huh. Could have sworn it was in there. Yeah, what is this word size C version? Okay, we'll go down to 4. Word. Is it not in this file? It says it's in the file. Oh, no, it's in the website. That makes sense. Vim, chapter 02, data. There we go. Do I need all these? Yeah, you can delete all that. Okay. Looks good. Okay. Alrighty. Go ahead and sign off here. Be on tomorrow morning. Later.